I'm really excited to be here and have a chance to share my work with you today as part of the CyCat seminar. I've never been to Cyprus yet, so I was Googling the images of Cyprus last night so that I can pretend that I'm actually in this beautiful country giving this talk. I'd like to acknowledge that my work is possible thanks to amazing students that I work with and generous funding from National Science Foundation and University of Texas at Austin. The context of my work is that AI is increasingly being integrated into workplaces and cities and take managerial and governance roles that humans used to make. So AI is not just deciding what we see online, Netflix or Google search, but they also manage worker routines, tasks, and incentives, and even who is offered jobs or small business loans. AI is also being applied in the criminal justice system, at least in the United States, and a lot of government programs. So given the high stake and large scale impact of AI in our society, many scholars have investigated techniques to enable fairness in AI decisions. So at the data level, there are numerous techniques that diversify and devise training data sets. And at the algorithm level, exist techniques add fairness constraints to machine learning algorithms or devise them. And these techniques aim to achieve distributed justice, ensuring fairness in outcomes. So for example, they will make sure that error rate in algorithmic hiring recommendations is same for both female and male candidates. And while this is an absolutely critical line of work, recent evidence also suggests that just focusing on distributed fairness is not enough to achieve AI fairness. People can perceive AI as unfair regardless of the distributed fairness techniques and AI's effectiveness. So I will go over much more details about why this might be happening later in the talk, particularly the first bullet points on the slide. But I wanted to give you an example of a real-world case where it shows that people could reject AI that they perceive as unfair despite its effectiveness. So in Flint, it's a city in the Michigan state in the United States. A poor water quality has been a long-standing issue, and one of the contributing reasons for the poor water quality is their old water pipe infrastructures. But however, the city doesn't have a complete record of which houses have lead pipes. So they built a machine learning algorithms to predict which houses are likely to have lead pipes so that they can replace them. And the algorithm was 70% accurate in the field, meaning that 7 houses out of 10 houses that the city digged up the ground actually had lead pipes. And this, in my opinion, was pretty good accuracy. However, the city residents pushed back the use of the algorithm because they thought that it was unfair, and they demanded that the city should start digging up every house instead of using algorithm recommendations. So the accuracy dropped to 15%, which means only 1 or 2 houses out of 10 houses that did the construction actually had lead pipes. So this example suggests that it is equally important to consider procedural justice in AI fairness. So procedural justice is perceived fairness of the decision-making process. And there is a long line of research on procedural justice in social psychology, which shows that it often plays as important a role as the actual outcome distribution in how people judge the fairness of the decision. So this diagram on the slide summarizes how the building blocks of procedural justice should be applied to algorithmic decision-making process. So in our work, we introduce procedural justice into AI fairness. We investigate how to explain AI decisions and give control to people. And we also explore how to incorporate stakeholders' concepts of fairness. So the AI systems are not built in silo based on just engineers' assumptions, but are co-designed with stakeholders so that the principles coded in the AI systems are in line with the stakeholders and community's priorities. So in today's talk, I will present 2 lines of research that we do to enable procedurally fair and participatory AI. In the first line of work, we examined what makes people perceive AI as unfair and untrustworthy. And particularly, we are learning that one of the main causes are because of people's late concepts of AI and the mismatch between AI's assumptions about the social context and actual social context. And in the second line of work, we propose and evaluate 2 frameworks to make AI to be procedurally fair and participatory. So I'll explain these in turn. So for the first line of research, I like to start by asking a question. So imagine that you apply for a job at Google and you later find out that your application was reviewed by an algorithm rather than a person. And how this knowledge of the decision maker influenced your perception. Would you feel that the hiring decision was fairer or less fair? So I cannot do actual poll here, but I hope that you actually thought about your own answers to the questions. And probably some of you thought that the decision was fair, and some of you might thought that the kind of having the algorithm scan the resume was not fair. And actually, when we did the study, we learned that the answer to this question it depends on the people and the context. But an important question here is to understand when and how these decisions are perceived differently. So when we did an online experiment to understand how this knowledge about the decision maker influences people's perception of the algorithmic decision, we learned that especially for tasks like hiring or evaluations, which people perceive that require unique capabilities of humans, algorithmic decisions were perceived as inferior to human decisions in all measures. So they are perceived as less fair, they perceived it as less trustworthy, and it evoked more negative emotions. And the majority of people mentioned that they have distrust in algorithm because they think that algorithm cannot sufficiently analyze some factors in place of humans, like considering personality or work culture, or they don't think the algorithm can forgive human mistakes. People did bring up the algorithm's objectivity. It applies the same procedure to everyone, but their concerns about the accuracy in the decision overshadowed procedural consistency. And what is also noteworthy is that the algorithmic decisions seem to evoke negative emotions and sometimes dehumanizing feelings. So for example, people said he would feel like a machine being chosen by a machine. So the fact that people are or even just can be evaluated by algorithm alone would seem to have a demeaning effect on the participants. So in the work that I just presented, algorithms are a complete black box. And the findings suggest that people's lay concepts, what they think algorithm can do or cannot do, influence their unfair perceptions of algorithm. And what will happen if we tell people more about the algorithm, like for example, saying that these algorithms are actually proven to be fair or can actually do these jobs? So next study that I will present explore this question in the context of fair division algorithms. Fair division algorithms are a subset of AI, computer theory, economics, and mathematics. the fair division algorithm takes input about people's preferences or needs or merit. And then they use those kind of individuals' utility, they use this individual input to understand how much utility people get from the limited allocated resources. And they allocate the limited resources to each person while maximizing each person's utility and meeting assumed fairness properties. So they are mathematically proven to guarantee fairness, which means that they satisfy different properties of fairness in all cases. So for example, the property of envy-freeness means that none of the player wants to swap their person with another because they find all the persons equally valuable. Another example is max-mean, which maximizes the utility of the person who gets the least among the group. Fair division algorithms have been used in a wide variety of domains. They traditionally have allocated computing infrastructure, such as network bandwidth or CPU resources, and they are now also being applied to more social domains, such as policymaking, organizational management, and healthcare and education. So to explore human perceptions of fair division algorithms, we use the website called Explicit. So Explicit is a website that applies fair division algorithms to everyday social choices, such as division of tasks, goods, or rent. And this provided us a nice experimental setup where we can examine human perceptions of fair division algorithm using real tasks. It also provides insight into what might be happening in settings like physician-residence matching, where fair division algorithms are currently used, but are inaccessible by the public. So using Explicit, I conducted 2 studies in which we brought people into a lab in groups and asked them to make division decisions using the features of the Explicit website. So on Explicit, each participant used the interface shown on the slide to input how much they preferred each task as compared to the baseline task. And they wrote a multiplier that is stating how many times they do one task to avoid another. An algorithm then assigned the task to each individual to minimize each individual's perceived burden with efficiency. Participants actually had to carry out the chores in the lab. So you can imagine that our kitchen lab was squeaky clean and smelled really nice for a few months as it was mopped and supplied with fresh coffee and lemonade every hour. So after the group of people finished the task, each participant filled out the survey and was interviewed individually. So what did people say after carrying out the chores assigned to them either by the algorithm or through discussion? So when algorithm divided the chores, participants thought that these decisions were only somewhat fair on average, and 40% of them thought that the outcomes were not fair. On the other hand, when people decided who was working what through discussion, they thought that the decisions were pretty fair. So overall, decision-based outcomes were generally perceived as fairer than algorithmic decisions. And the interview suggests that the gaps between the algorithmic assumptions and the actual human behaviors contribute to this perceived unfairness of algorithmic allocation. So fair division algorithm implement equity-based fairness using individual preferences so that in the best case scenario, each participant gets the task that they like most. However, participants had a more diverse concepts of fairness. Some prefer equality, everyone getting just the same amount of tasks, or getting tasked randomly, regardless of individual preferences. They also had varying definitions of utility. So for example, some wanted the algorithm to consider additional factors such as individual skills or the time that each task takes, so that in the best case scenario, the quality or duration of task is also optimized. The splitted algorithms also assume that individuals are rational actors who want to maximize self-benefit. But in reality, in our context, some of our participants were willing to compromise to help others. So they value the happiness of the group as well as their own, and they wanted to accommodate others' needs. So these people wanted the algorithm to consider these factors or at least support these behaviors. So for example, one participant said that he wanted the software to collect the reasons why different people wanted certain options, so that he could decide whether to alter his share depending on the reasons. So in this first two studies, I explained what makes AI to be perceived as unfair and untrustworthy from human perspective. Then the second line of research focuses on mitigating problems observed from the first two studies. And specifically, I explore ways to incorporate procedural justice in algorithmic decision-making and empower people to design AI services for their own context. And I will explain these in turn. So this is a framework that I briefly introduced in the introduction of this talk. So to kind of think about how to incorporate procedural justice into the AI decision-making process, we reviewed a literature on procedural justice from social psychology and organizational behaviors. In drawing from their the literature review, we categorized the three important components and principles that can be mapped into the process of algorithmic decision-making. So what kind of input they're getting, what algorithm is used, and how their decisions are communicated. So the transparency components talks about we should make the standards clear, show why the standard is valid, and whether the information that are being used is representative. And also it says that there should be explanation of the outcomes. There is a control component where people can control the decision-making process itself, which is about input and algorithm itself, and whether they can actually control the outcome. So whether they can change or refute the outcomes that they are getting. And then the third layer of this framework is that in general, regardless of whether the process is transparent or whether people can control, people's beliefs about the decision maker itself, whether they think they have a good intention, whether they think the procedure is applied consistently, whether they think the decision maker is competent, etc., is holistically all contributing to how people perceive the fairness of the algorithmic decisions. So once we made this framework, we wanted to empirically examine the different components of this framework, particularly with a focus on the transparency and then outcome control. So going back to the study, fair division algorithm study that I was talking about earlier in this presentation, we went back to the system and we added interfaces that can explain how the fair division algorithms are making decisions, and then allow the participant to actually control the division outcome that they're getting. So to add the transparency, particularly to explain the standards, meaning like how fair division algorithm work, we created this diagram so that they can actually know how the fair division algorithm use individuals' input and how it tries to divide the utilities that people are getting from the goods that they're getting assigned. we also explain the outcomes that they're getting by showing the actual utilities that are assigned to different participants, different resources or goods. So you see, we use this table-like format where people could see how much utilities they're getting from each resources, etc. And then we allow people to be able to explore alternative divisions by clicking these other cells here. So for example, the blue box here shows the initial algorithmic allocation, and this green box shows that the current allocation outcome means that you can change this resource 4 to be assigned to person 2, and you can see how that affects the utilities that each individual is receiving from this allocations. So we ran another study exploring how the added transparency and control impacts the perceived fairness. So in the study, we looked at kind of group people based on their initial perceptions of the outcome. So that's a baseline. So these are groups of people who initially thought that the division outcome that they got was fair. And these are groups of people who thought that the outcomes that they received was unfair. And when we showed transparency, we saw that it marginally improved the perceived fairness, but the effect was very small. And it actually decreased the perceived fairness of the groups who initially thought that their outcomes were fair. And then we saw that adding the control universally increased the perceived fairness for everyone. So we learned that from this study that the transparency itself is not enough in terms of just increasing the perceived fairness. So we learned that the reason why it didn't really improve the fairness is that for people who initially thought that their outcomes were less fair, sometimes they actually learned that they got less utility than the others. So actually it kind of made it salient that there is an unequal there could be unequal distributions of goods or resources in this allocation. So it in itself did not improve the transparency, but it also helped people to see whether the allocation is actually equal or it's a less equal. Because one thing to note is that because these are resources and goods, it's not a money. So even though the fair division algorithms are in place and it tries to maximize each individual's utilities, still it cannot be perfectly equal, meaning that the utilities that each individual is getting, the number will not be, in many cases, it can't be the same. And then what was interesting was that people who initially thought that their outcomes were fair, they also realized, they said that they initially assumed that everyone else would have received the best outcome as well. But then they also saw, actually, they got the really good deal, but then not everyone got the good deals that are as good as their ones that they got. So overall, transparency made salient about what was happening, but it didn't really improve the perceived fairness. But the control, or the ability to kind of having a chance that they can actually change the outcome, universally improve the fairness. And it is interesting that actually only 22% of the group changed their outcome, and the rest didn't change their outcome. But just having an opportunity to control the outcome and voice their concern itself improved the fairness. And what's also noteworthy here is that oftentimes when they try to come up with a better allocation outcome, they realize that also they couldn't do that either, because sometimes it's just inherent there is an inherent limitation in the context that the way people's preferences are distributed, this is as fair as it can get. So by trying to control the outcome themselves, they could better realize the limitation of the context, and they felt more empathy toward the algorithm that are making these kind of decisions. So in this project, we went over, particularly when people have transparency in the decision-making process and outcome, and how the control over the outcome could improve the perceived fairness of the algorithmic decision-making. So in the final study that I'm going to go over, we came up with a framework that allowed people to actually have control over the algorithmic decision-making process. In other words, they can control the kind of information that the algorithm could use, or what should be the, for example, objectives of this algorithm, so that they can actually have the control over how algorithm is making decisions, not just the outcomes that the algorithm is giving to these participants. So in this final framework, our approach is that we wanted to enable collective participation of stakeholders in defining these algorithms. And when I say defining algorithm, as I said, is setting algorithmic objective functions or kinds of information that the algorithm should use. So specifically, we propose a framework called We Build AI. So the key idea of the framework is to build a computational model representing each individual stakeholder, and to have that model negotiate or vote on its individual's behalf. So this works like a group of people making a decision together, as I said in the allocation study in the first part of this talk. But instead of an individual themselves, virtual computational models of each individual's decision-making process will make a group decision for each algorithmic decision. So in this framework, we first define what information or features should be used in decision-making with these stakeholders. Then individual stakeholders create computational model that represents their beliefs by training a machine learning model or manually specifying a scoring model. Once stakeholders create their model, the models are embedded in the AI system. So for each algorithmic task, each individual model will rank all alternatives, and this individual ranked list will be aggregated using a border scoring method to generate the final ranked list. And finally, the ranked recommendations are explained to stakeholders to support operational decision-making. So to make this more concrete, I'll explain how we use this framework to build a matching algorithm for an organization called 412 Food Rescue, an on-demand donation transportation service that are operating in the United States. So let me first explain how this service works. So 412 Food Rescue is like Uber for charities. So they take food donations from donors such as grocery store, restaurants, and retail stores, and they allocate them to nonprofits that help underserved, food insecure communities. So examples include food pantries, homeless shelters, and public housing communities. They use an app to coordinate volunteers to pick up and deliver donations to the nonprofit. And the organization has been quite successful. They work with about 800 donors and recipient organizations and have a pool of thousands of volunteers. And they are expanding their model into other cities, other than Pittsburgh. So these other cities include San Francisco, Philadelphia, etc. So this organization wanted to introduce a algorithmic matching system for two reasons. They only have a few human employees manually allocating donations, and they're overloaded. So they like to offload their dispatcher's workload. And another reason is to improve equity in their donation distributions. So current donation distribution is quite skewed, with 20% of recipient organizations getting 70% of donations. And it's because the allocation decisions are often made for convenience. So the human don't have time to keep track of which donation is going where and use that when they have to make decision under time pressure. So in designing this matching algorithm, we specifically focused on using collective participations to determine the trade-off between equity and efficiency. Balancing equity and efficiency is a fundamental challenge in a capitalist democratic society, and it requires a normative approach. So in other words, a human needs to define how to balance these competing factors, and there's no fundamental right balance because it can't be determined purely through optimization. And balancing equity and efficiency comes with challenges as this design choice can have very different impacts on different stakeholders. So for example, let's say that these matching algorithms prioritizes efficiency and gives donations to recipients closest to donors. And it will be very convenient for volunteers because they don't have to drive long, but it also means that donation distribution will be skewed and recipients in wealthy areas may get more donations because donors are often located in wealthy areas in the United States. On the other hand, if these algorithms prioritize equity, recipients with greater needs may receive more donations, but this may increase the distance that volunteers need to drive, as well as the effort One to Rescue must spend in recruiting the volunteers. So finding a collective solution to this trade-off is critical to the success of the service, as well as we think that all stakeholders will be more motivated to continue participating in the service if they feel that their needs are respected. So to this end, we use our framework to build the allocation algorithm collectively with 4 types of stakeholders. And our participants provide feedback at every step of the process and also help to build the algorithm by creating their own individual models. So I'll now walk you through each step of our framework application. The first step was to determine what features or input information that algorithms should use based on the feedback from the stakeholders. So for this, we conducted interviews with them to understand what factor they thought the donation allocation algorithm should consider. So from the factor that they mentioned during interviews, we selected ones that came up most frequently and that had reliable data sources. So for example, poverty rate was mentioned as one indicator of clients' needs. Distance between recipients and donors are often mentioned as a metric of efficiency. And we also wanted to consider when each recipient last received donations so that we can use it to define allocation patterns over time. And next, we use these features to model people's individual beliefs. We use 2 methods interactively. So the first method was machine learning based. So we presented pairwise scenario that shows 2 recipient organizations that varied along the factors that were derived from in step 1 and asked people to choose which organization should receive donations. So they were asked to choose whether recipient A or recipient B should receive donations. And they answered about 50 pairwise comparison questions. And then using that answer, we use machine learning using a random utility model to train an algorithm to learn how people weighted the different factors. And we experiment with diverse techniques for learning utility model. But at the end, linear regression yielded the best accuracy, and it was the simplest to explain. The next method was the explicit rule specification. So in this method, we actually asked people to just explicitly write down the score or weights for each factor. So this was an explicit design decision for us because we wanted to also give them a chance to see what they think is important and whether they are developing consistent rules. And we use these scoring models instead of decision tree, etc., because scoring model also capture the method of balancing factors that people identify when answering the pairwise comparison questions. Once participants had completed both models, we showed them the two models in a graphical form and asked them to choose one that best represented their beliefs. So in this kind of a graph, for each feature, like the travel time, which is a distance, and then or the client organization's poverty rate, like the neighborhood that client organization exists, we show the assigned score along the input range for each feature. And in this model, the higher score indicated stronger recommendations. And we then asked people to choose a model that better represent their decision making. Just to prevent any potential biases, instead of saying which model or machine learning versus one that they actually created, we anonymize the model name, calling it model X and model Y. Yeah, and this is showing the actual model that people actually built. And for this participant, it was remarkable that the model that we learned through machine learning versus explicit rule were very similar. They were following the same trend. And for distance, it was almost the line overlap completely. It's interesting that for this participants, the model that we learned through pairwise comparison versus explicit scoring rule, explicit specification model were very different. So this was actually the organization's employee, and she told us that when she was answering pairwise, which is a blue line, she was focusing on more real-world constraint. How can I recruit volunteers fast? But when she was actually explicitly kind of giving weight for different features, she said she was more idealistic. So she wanted to really prioritize areas with lower income, higher poverty rate, in areas with a high food, like low access to food. It's called food desert. So at the end, after seeing these models, she chose her blue model, which is model driven from pairwise comparison, because she thought that at the end, the operational efficiency is very important. But this also suggests that maybe the way that that we're eliciting these kind of individuals model could also have an impact on what kinds of model that we are getting at the end of the elicitation process. So we implemented the model that each participant chose in our system. Just want to highlight that in terms of the model's accuracy, we learned that overall machine learning model was more accurate than the explicit rule specification model, but for some participants, explicit rule model was much more accurate. But so once participants chose the model they wanted to use between the two models that they created, we implemented that into our systems. And then in our step 3, we aggregated the outputs from these individual models. So specifically, when there is each incoming donations, each individual model that people created create a ranked list of potential recipient organizations. And these individual lists were aggregated using a voting rule to create the final recommendation list. So in the final step of the framework, we explain these algorithm recommendations to kind of participants, and then in the real world to support the organization's operations. So we explain the overall voting score that each recipient organization received So this was like a maximum votes that they could receive, and they got 128 out of 136. These were kind of a ranking of this recipient depending on their stakeholder groups. And also we showed what factors contributed to the recommendations. So, and we built the interface to integrate this recommendation system into their the system that the organization uses. So when they click the show recommendation, when there is donation, it shows the list of recommended organizations. It shows why this organization is recommended, and it shows how this was ranked, organizations ranked by different stakeholders, etc. Okay, so this step concludes the algorithmic building process. So for the few minutes that we have, I will quickly go through what we learned through this process. And what are the effects of participation in algorithmic building, and then looking at what are the impacts of this algorithm on the actual donation distributions. So one of the reasons why we wanted to include the stakeholders in determining this allocation algorithm was that we thought that this will be a way for people to kind of input what they think is important, and then we thought that that participation will make people think that this algorithm is actually fair. And we learned that actually our original assumption about this approach was kind of correct, in that a lot of people, like everyone actually who participated in this process, said that yes, the algorithm is really fair. This is as the most fair that you could get. And they also thought that the organization using this algorithm, the organization was also fair because they're not just building this algorithm inside their organization, inside their bubble, but the fact that they are talking to stakeholders was appreciated a lot by these stakeholders. But one thing that we were not sure in the beginning was how this algorithms will actually lead to kind of what kinds of distributed outcomes. So we ran the simulations. So using the 5 months of historical donation data, and we compared it with the decisions that humans made, which is the orange line, and then what allocation the algorithm will make if this algorithm was used, I guess, for the same period of time. And we saw that you see that donation was very heavily skewed with the human, as I mentioned earlier, by the human dispatcher. The algorithm made donation to be more evenly distributed. And we see that the algorithm is giving donation to recipient with a higher probability rate compared to humans. And then we also saw that one concern that we had was what if this algorithm is always giving to organizations that are far away, which will increase the transportation and travel distance. And we saw that actually algorithms did not increase the distance, and overall the difference is small, but actually it decreased the accumulated distance of the overall rescue compared to what human allocation have been like for 5 months. And then the final point that was unexpected for us, that the experience of making individual model itself had a significant effect on participants, particularly on their awareness of what they think algorithm can do and what they think about the governance decision overall. So this process of building the algorithms or pairwise or just even simply scoring them, we found that participants became more accepting and less resistant to the idea of using algorithms. So one surprising moment for me was that when one participant told us that, unprompted, that he actually now believes in algorithm wholeheartedly. And he told us that he was actually very skeptical in the beginning that an algorithm could make such a complex decision that involved caring for others. But then after going through the step-by-step process and then actually seeing how the algorithm that he built predicted his own decisions, he told us that he now believes that algorithm can make such decisions. The other kind of unexpected finding for us that people said they are more empathetic and they understand the organization decisions that the organization make more, because they, as they went through this process of making decisions, they realized that there might not be one perfect solution. So they said that they understand the difficulties of this organization. And this is an important change because it can improve people's tolerance and understanding of trade-offs that are inherent in any governance decisions. And the final kind of point is that we did also this activity with the 3 staff members in the organizations. And what was interesting that they had their own internal guidelines on donation allocation. They thought that they're making consistent decisions as a group. But when they actually built this model, they were surprised that their models varied in the ways that they weighted poverty, organizational size, and distances, etc. So this process helped them to kind of make their own decision-making process to be more explicit, so that we can learn the inconsistency in their organizational practices. So to summarize, our framework allows people to collectively build an algorithm for their own context. And the application shows that the collective participation can lead to AI that better reflects the principles that these stakeholders value and find fair. And individual model building process can improve the algorithmic awareness. So overall in the talk, I presented what makes AI to be perceived as unfair and untrustworthy, and presented a procedural and participatory framework that could make AI fair and trustworthy. And to wrap up, I'd like to go back to the very first study that I presented. So in that study, people perceived that algorithmic hiring was less fair and trustworthy than human decisions. But what surprised me most there was that people they trusted human managers more than the algorithm because they trusted the human system, not because they thought that humans were inherently fair. They also mentioned that the manager, I can trust manager because I'm sure the organization promoted them to be manager because they trust the organization trusted those humans, that person's capability. So kind of if we look back our history, when manufacturing machines were first introduced to the workplace, the Taylorism was developed to optimize human behaviors around them. And it took many more years to create a management style that was not only efficient, but also motivating and enjoyable for human workers. So as algorithms begin to enter our society, it is our responsibility to make sure that we can have a trustworthy and good systems for AI, not just for human bureaucracy, so that we have safeguards, regulation, and evaluation mechanisms, so that human experiences remain a priority even in the workplaces and cities that are using AI. Thank you.